In this video, we're going to be discussing the concept of chemical catalyst and ozone and these two concepts' relation to the harm of CFCs, which are compounds that were previously discovered to be destroying the ozone layer through a series of chemical reactions. Okay, so here we have the concept of chemical catalysts here. We're going to start off by discussing how these catalysts work with the CFCs to destroy the ozone layer, as they were discovered to be doing. So a chemical catalyst, first of all, is something or a molecule usually or an element that is added to a reaction to speed up the reaction without itself being destroyed. So usually that catalyst is preserved after the reaction finishes taking place. So it's still there to continue speeding up the reactions. Now, usually this speeding up is done by increasing the energy of the atoms going into the reaction, or sometimes it also directly decreases the activation energy of the reaction, which we're going to get into what the activation energy is a little bit later when we get into the more advanced parts. Okay, so here we have the chemical catalyst of chlorine. So when chlorine is the catalyst, we're going to have some strange things going on with the atmosphere. So, for some context, we have oxygen to ozone is the fundamental reaction that happens all the time in the atmosphere. So what we're going to have is basic molecular oxygen and through UV, ultraviolet rays, coming together to form ozone. So here's our product here. These are the reactants, and these are the products right there. So that's totally normal, that's expected, there's no interference going on right now. Then the next step is the ultraviolet rays converting to heat through ozone. So you can see the ozone allows the UV to change into heat because it's still the ozone here, it's just the UV is morphing into the heat. So that's not a completely normal reaction. We have the UV transforming into heat, which is heats up the atmosphere through the UV rays. Then we have step 1 of the chlorine reaction itself, and this is where the chemical catalyst of chlorine comes in. So linking back to the CFCs here, so CFCs are a volatile organic compound that's emitted into the atmosphere, typically through aerosols or any other refrigerants sometimes will emit those. The harmful refrigerants that emitted the CFCs have since been banned and outlawed completely. But over the past few decades, they were playing a serious role, especially in the 80s and 90s. These CFCs were causing a serious problem. So, and here's why. We have step 1 of the chlorine reaction. And the CFCs contain a compound that will speed up the destruction of ozone through chlorine. So we have chlorine here, which reacts with ozone to get rid of the ozone entirely, and instead you have chlorine monoxide and oxygen only. So as you can see here, the ozone has gone out the window. Via the chlorine, we're destroying the ozone molecules. And you'll notice here the chlorine is preserved after the reaction. We have chlorine shows up yet again here. And the reason for this is because, well, chlorine is the chemical catalyst right here. It helps to speed up this reaction in step 1 here, which is why the ozone goes away faster and makes a hole. And step 2, we still have the chlorine. So the chlorine destroys the ozone, comes back, destroys yet more ozone. So that's why chlorine, as a chemical catalyst, as a result of CFCs, is so harmful to the environment because it's destroying the ozone layer, which exposes us to much greater UV levels, because the ozone layer is there to protect us from the UV rays coming in from space. Okay, so now here are 2 graphs for the activation energy before and after chlorine starts going in there and messing things up. So on the left here, we have without catalyst. This is things as normal, but without chlorine going in there. So the activation energy, to clarify here, is the amount of energy the reactants, such as the ozone, must have in order to react to form the products, or the oxygen right here. So as you can see, the activation energy, or EA, is represented by this hump here, where you have to go up and then you have to come down. The going up part is the energy these reactant molecules over here must have in order to react to form oxygen. So they must get over this curve. They must have a certain level of activation energy. Otherwise, they're not going to react at all. Okay, so this is a pretty steep curve here. As you can see, you must go all the way up in order to form the products. But then, chlorine comes into the equation, literally. We have chlorine catalyst adding itself, and as you can see, the hump is significantly decreased now. The energy is much lower. There's only a tiny bump compared to the first graph over here. And this means that the ozone molecules no longer need as much energy to form the oxygen. So you're going to have ozone converting to oxygen like crazy. The reaction is going to be happening at super speeds, because the chlorine catalyst has significantly decreased the amount of energy required to convert to oxygen. So as a result of that, you're going to have a significantly increased level of reactions there, and you're going to have a lot more oxygen and a lot less ozone. The ozone levels are going to quickly deplete, which is why you always hear about the hole in the ozone layer, because the chlorine catalyst is going in there and messing up the reactions and just totally taking the ozone out of the picture due to that changed activation energy. Okay, so there it is, the summary of CFCs, chemical catalysts, and their harm to the environment here. In this video, we looked at the different stages of reactions here involving the chlorine catalysts, the oxygen to ozone reaction, then UV converts to heat, then steps 1 and 2 of the chlorine reaction, where the ozone is completely cut out. Okay, and that's the overview of CFCs and chemical catalysts.